Hello everyone, and today I'll be talking about intersection of sets. In fact, in this video, I'll be taking some numerical problems. If you want to understand what does the intersection means theoretically, so you can see the previous videos. But at least let me give you a Venn diagram exactly how the intersection works. And I'm going to talk about the intersection of two sets here. If there is this set called X, and I'm calling this particular set as X, and there is another set which I'm calling as Y. This is set Y, and I'm intended to understand what is X intersection Y. So this shaded portion represents the intersection of sets. Can rewrite it here, X intersection Y is this shaded portion. Or probably you can think of the common area between the two sets that becomes the intersection. So let's pick up some numerical problems. And the first problem which I'm picking up is, if let us suppose an X is a set which is given to you 1, 3, and 5, and there is a set Y which is given to you and it can be written as 1, 2, 3. So there are three members in set X, three members in set Y, and necessarily you want to know what is X intersection Y. And simply you have to see that what are the common elements between them. So I see one, the one exists in X. Is it in Y? Yes, it is in Y. 3, does it exist in X? Yes. Is exist in Y? Yes, it is. But 5, if you see, it exists only in X, but it doesn't exist in Y. And same way 2 exists only in Y, but not in X. So how do you write it, the common elements? It is going to be 1 and 3. So these are the two elements that are going to belong to this particular intersection. And if you want to draw a Venn diagram for this, that is going to be very simple. So you have a universal set, then you have a set X, and then you have got a set Y. And here it is 1 and 3 lie somewhere here. While in X you see there is one extra element 5, and in Y there is an extra element called 2. So this is the Venn diagram. If you want to see, this is X, this is Y, and this diagram is representing X intersection Y. So you can see that the common elements that are exactly being taken care of here. Let's talk about another example of how exactly the intersection of set works. So if I'm saying, let us suppose you have been given a set called A is equal to A, E, I, O, U, and you can see this is a set of vowels simply. I've got a set B, which is saying you A, B, and C. And I hope it is very easy to spot what are the common elements. A is in A is in B, and E is in A but not in B. I is in A, not in B. O is in A, not in B. U is in A, not in B. So if I see A intersection B here, the common element here is A only. So it's a singleton set A. That is exactly what A intersection B is about. And you can simply think about it. If I'm going to draw a Venn diagram here, then this is set A and this is, let's say, the set B. Then A actually lies here, that means in the common area, and then E, I, O, U, and B and C are exactly here. So you can see the shaded portion becomes at A intersection B. So this is set A and this is set B. So that's another problem. Let's go for one more problem. Let's see exactly how different problems can be solved. If I have a problem here that says A is a set and it is being said that X such that X is a natural number. So X is a natural number. So I will say natural number and it's a multiple of 3 and multiple of 3. Multiple of 3, that is A, and there is another set B which is being given by X such that X is a natural number less than 6. So that is what do I have. So first these are the set builder forms. What I'm going to write is I'm going to write the the tabular form of them. So X is that X is a number, a natural number and multiple of 3. So many students are confused. How do you write the multiples of 3 or any number as a matter of fact? So how do you write the multiple of 3? You first write 3 times 1, then you write 3 times 2, then you write 3 times 3, and so on. You continue. So fundamentally, any number, if you want to write the multiple of 5, it is going to be 5 into 1, 5 times 2, 5 times 3, and so on. So what are the multiples of 3 and natural number? It is going to be the first multiple is 3, you can see right here. The second multiple is 6, you can see right here. Third is 9, and so on. You keep on writing these particular numbers and so on. And if you set C set B, it is a natural number which is less than 6. So what are natural numbers? Start from 1, then goes to 2, then 3, then 4, and then 5, up to 5. Why I'm counting till 5? Because it is less than 6. And obviously I want to know a intersection B, and you can see what is the common element between them is 3, right? And since this set is up to 5 only, so this is the only common element, and the intersection B can be given here by 3. And again, if you want to sketch a Venn diagram from this entire concept, then this might be a set A, which has multiple elements, and this is set B, and which there is a 3 which is common right here, and and there are rest of the elements in B which are 1, 2, 4, and 5. And here there are multiple elements like 6, 9, and 12, and so on. There are many more elements in that. So this is set A, which is actually representing the multiples of 3, and this is set B, which is representing natural numbers less than 6, and this portion here is actually representing A intersection B. Let's see more examples of how actually the intersection of sets work. So I'm taking another set which is saying me A is equal to, this is example number 4, x such that x is a natural number, so I can write it something like this. X is a natural number, and 1 is less than x is less than equal to 6. So that means x is lying somewhere between 1 and 6. If I see set B, it is x such that x is again a natural number. So I can again write it, x is a natural number, and 6 is less than x is less than 10. So if you see how do you write the elements of this set, that becomes very, very important. So A is equal to, if you see x as that x is a number now, and it is between 1 and 6. It is greater than 1 and equal to 6. So it is going to be 1, 2, 3, 4, 5, and 6. These are the members of A. And if you write set B here, that is simply going to be, it is actually x is above 6 and less than 10. So I'm going to start it with 7, 8, and 9, 3 elements, because it is less than 10. That means 10 is not included. And if I want to write A intersection B here, you can see there is only one, no common element in there. So it is going to be an empty set, and it can be represented by 5. So that is exactly how A intersection B can be written in this particular case. And if you want to sketch a Venn diagram out of the A and B, then you can simply say this is A and this is B. Nothing in common, right? So this is A, set A, this is set B, and their intersection is phi. So this is simply A intersection B. This is what I'm trying to calculate, which is phi in this particular case. Let's see some more examples, and I would be looking into example number 5 now. And the fifth example says if A is equal to 1 to 3, that is given, A is equal to 1 to 3. And if you say set B, this is exactly 5. That means nothing in it. So if ever you find intersection with any null set, that becomes a null set itself. So it is a kind of a remark which you can note, and you can use this particular result directly, that what exactly is a intersection B. Let's see some more examples. I'm going to write now something like, I'm going to take 3 sets A, B, and C, and what I'm going to do is I'm going to just check out that how exactly different intersections between A, B, and C works. In fact, I'll take the 4 sets. So let's see, if I have been given with a set A which has certain elements, which is 3, 5, 7, 9, and 11. I've got another set B which says 7, 9, 11, and 13. And then I've got a set C which says 11, 13, and 15. and I've got another set D, which is exactly 15 and 17. So four sets are given. Now I'm going to find certain inputs. The first one is actually what is going to be A intersection B. And I'm going to find the common elements between A and B. You can simply see 3. No, it doesn't exist, so it doesn't go in A intersection B. 5, does it exist in B? No, doesn't go in the common list. 7, does it exist? Yes. 7 is in A, 7 is in B. 9, yes, it exists, so it is going to go in the kitty once again. And 11, yes, also it is. So A intersection B here has 3 elements, 7, 9, and 11. The second portion of this particular question you can think about is, let us suppose I want to find out B intersection C. So if you see B, 7, there is no 7 in it, so it doesn't go in the common elements. 9, there is no 9 in C, doesn't go in common elements. 11, yes, there is an 11 and there is a 13 also. Well, 15 is there in C but not in B. So I'm going to write it 11 and 13. You can see that. So same way, let us suppose I'll do a particular example that asks me what is going to be A intersection C intersection D, let's say. So simply what I'm going to do is first I'm going to find out A intersection C, and then whatever the result comes out, I'm going to find its intersection with D. You can do it other way around also. You can also do something like A intersection C intersection D. That means you find out C intersection D first and then find the result to A. But I'm going to follow this first particular part here. So this is also what you can do. So if I'm going to do that, first I'll find out A intersection C. So if I see A intersection C, 3, it's not in C, 5 is not in C, 7 is not in C, 9 not in C. So fundamentally this becomes a 5. Or okay, no, 11 is there in A and 11 is there in C. So I find an element called 11 here. Now I'm going to find its intersection with D. What is D? D is 15 and 17. So if you see, there is nothing common between these two sets here because it has 11, it has 15 and 17. So it becomes a null set and you can also write it as 5. Let me do one really good example and I'll try to find out. And this is also called as a distribution law. So I'm going to find out A intersection B union C. This is what I'm going to do. So intersection is distributive over union. So that means this you can write simply as A intersection B union A intersection C. And I just can give one simple example. You have got something like, you know, x times y plus, let's say, z. So you write something like x times y plus x times z. So multiplication is distributive over addition. So same way you can call it that, intersection is distributed over union. So let us find A intersection B first of all. What is A intersection B? I have already solved it here, 7, 9, and 11. So I know it is 7, 9, and 11. Then I've also solved A intersection C here, which is simply 11, union 11. Now here you have to be careful. Union is different from intersection. I have to write all the elements of A and all the elements of this particular portion 7, 9, 11 and of the other portion 11, which are non-repetitive. So the union is going to be 7, 9, and 11. So this is the answer. This is also called the distributive law. And thank you very much. Let's meet in the next video.